annual meeting that focuses on the Arctic sea ice minimum that typically happens in September. And so the goal of today's meeting is to focus a little more broadly on understanding the state of the Arctic sea ice cover from a variety of ways of observing. So we have kind of two sets of presentations. The first focused on satellite observations of the sea ice minimum and updates on sea ice indices from our two presenters from the NSIDC and UC Boulder, Walt and Anne. And then the second half, we'll talk a little bit more about community and Indigenous observations facilitated by the SIKU app by Joel Heath at the Arctic Eider Society. Before we get started, I just want to mention also some of the other upcoming meetings that we have. So next week, we're planning to have a listening session related to the Arctic Research Plan draft that is co-hosted with a bunch of the other community of practice, and that will be on Wednesday, assuming if the government has reopened. Also next month we're hosting a meeting on sea ice thickness. The date has not yet been fully decided, but should cover both sea ice observations and modeling perspectives. And so if you're interested in that, keep an eye on the announcements in your email or on the IRPIC page for the determined date on that. So with that, I'll hand it off to our first speaker, who's going to be Walt. And yeah, thanks all for being here.
All right, thanks, Maddie. I'm going to share a screen, and then actually, so Anne Windnagel and I are co-presenting, and Anne is going to start off for us. So go ahead, Anne.
Great. Thanks, Walt. Yeah, so we're just going to cover briefly summer ice conditions and the September minimum. That's what Walt will cover. I'm going to cover some sea ice index updates first. The main thing being transitioning from the SSMIS sensor to the AMSR2 sensor that we had to do this summer, as SSMIS data will be going away fairly soon. Next slide. Great. This is going to be fairly high level, brief introduction to what we did and why we did the transition. If you have more questions or want details, please contact Walt or I, and we can give you more in-depth science details and technical details on this stuff. Next slide, please. So first, I'm sure everyone's pretty familiar that if you want to create a long-term record, you got to put together satellite data from satellites that span many years. Satellites don't last forever. They fail due to the sensor just failing, batteries dying, satellite control fails, runs out of fuel, mission is defunded. Those are just a few of the things that can happen. Earth observing satellites generally have a 3 to 5 year lifespan, but they sometimes can last much longer, and they often do. I'll show a slide of the lifespan of some of the SSMIS and AMSR2 instruments, and they've continued on well past this 3 to 5 year. But again, to create that long-term record, we've got to stitch together these multiple sensors. Next slide. And so to stitch them together can be a little bit of a challenge. Every satellite and sensor is different, even ones that are built to be exactly the same, like the suite of SSMI or SSMIS sensors from the Defense Meteorological Satellite Program were meant to be as similar as possible. They still have different, altitudes or orbit crossings, or their calibrations ended up being slightly different before they were launched. So you need to bring these sensors together, doing an inter-sensor calibration, or intercalibration for short, to assure consistency as best as we can through the record. The most common way to do this is to compare data from both sensors operating in orbit at the same time, and where they overlap. So you can compare overlapping data. Next slide. So then specifically this summer, I had to transition sea ice index from the SSMIS sensor to the AMSR2 sensor. Next slide. This is just a quick graphic. The Blue bars are satellites from the U.S. Department of Defense. Red is from JAXA, and the green is European satellites. We can see that our SSMIS sensors have been around for quite some time, well past their 5-year lifespan. We had begun planning a transition to the JAXA AMSR2 quite a few years ago, knowing that any of these SSMIS sensors could go down at any time, given that they were fairly long in the tooth. So when yes, so and then so we decided to switch to AMSR2 because that's what's available right now. AMSR2 actually is also getting quite old. It was launched in 2012. AMSR3 has recently been launched. I don't believe data has been released from that quite yet. I think maybe they're doing tests of it. And then, of course, there are follow-ons for the U.S. Department of Defense from the Weather System follow-on, the WSF, and the European Space Agency has some satellites coming later in the decade. Next slide. So this, oops, one too many. There we go. So we in May, we started seeing the imminent end to SSMIS. We were seeing large gaps in the daily data. We were informed by the Navy that the SSMIS was going to be reduced, the support for it was going to be reduced, and the DMSP program official ending date is September 2026, with standard data availability ending before October 2025. Basically, the data will be available through 2026, but only on a quote unquote best effort basis. So it's no longer a priority for the Department of Defense to continue to run this. So we expect large gaps for the next year. So that informed our decision to go ahead and switch to AMSR2 for the near real-time sea ice products, specifically sea ice index. Next slide. And so for those who might not be familiar with sea ice index, it provides a quick look at Arctic and Antarctic-wide changes in sea ice, and is a source of consistent, up-to-date data on sea ice extent and concentration. We provide both images and data files in CSV and Excel. It uses the NASA team algorithm for its sea ice concentration computation. The sea ice index version 3, which is what we were just in, used the SSMIS sea ice SSMIS brightness temperatures. Actually, I should say brightness temperatures and not sea ice concentration. And then, or is that? No, yeah, sorry. It used the sea ice concentration. And then we switched to AMSR2 concentration for the version 4. Just keep those in mind when we get to a couple of the graphics and slides. They say V3 and V4. I'll remind everybody, V3 is SSMIS data, V4 is AMSR2 data. And then also, for those who don't know, sea ice index is the main data for the Arctic Sea Ice News and Analysis blog that NSIC puts out, now called Sea Ice Today. And so it gets a lot of attention, especially down around the minimum. Next slide. So what are the challenges of the SSMIS to AMSR2 transition? So, of course, sea ice is of particular interest for climate records. And we generally use extent. You'll see, everyone sees graphs of extent of the retreating ice as time has gone on. Extent is a thresholded quantity, so it's ice or no ice. So sensitive to small changes in concentration. The concentration threshold that's generally used is 15%. So 15% and above is considered ice. Anything below that is considered not ice covered. And that is because values less than that for passive microwave data tend to have a higher uncertainty. So we trust 15% and above and not the lower values. The transition to AMSR2 is a little more complicated than our previous transitions. So SSMI to SSMIS, because AMSR2 has a much higher spatial resolution than the other sensors did. So what NSIDC decided to do, we were using resampled AMSR2 brightness temperatures from JAXA, the JAXA L1R brightness temperatures is what they're called, that are as close to the SSMI resolution as possible. And then NSIDC took these L1R, this L1R product, and we gridded it onto our 25-kilometer polar stereographic projection grid. And we used what's known as just a drop in the bucket method, or a simple sum and average method to fill the grid. So you see a picture here, in the graph, you see SSMIS for each of the channels has a much higher, lower, more coarse spatial resolution than AMSR2, but then the L1R resampled gets it to be a little bit closer to that of SSMIS. And then the graphic on the right shows how one grid cell or one footprint of the SSMIS 19.3 gigahertz center, 9 of the AMSR2, effectively 19 gigahertz channel fits into that. So that's what makes it a little more challenging to intercalibrate the two. Next slide. So we did a few other things besides just taking the L1R data, because it got things close, but not quite there. So we did a linear regression of the brightness temperatures between the old sensor, SSMIS, and the new sensor, AMSR2, and did a slope and offset adjustment. For the NASA team algorithm itself, we adjusted the tie points of the pure surface ice and water tie points for AMSR2 so that they matched SSMIS better. And then further for AMSR2, we did a Gaussian blurring or resampling to do some additional smoothing on the brightness temperatures to have it match SSMIS more. And again, I'm really glossing over the fine details here, so if you're interested in them, please contact me or Walt after. Next slide. And so here's what we get. Differences are mostly at the ice edge and near the coast, which kind of makes sense. You know, AMSR2's higher resolution, it sees the ice edge in a different way than SSMIS, but it's fairly minimal. Here, the blue is AMSR2 only. The kind of magenta colors where SSMIS only sees ice. The gray is both, and then the yellow is where there isn't any data. And then next slide. And here we have more of a real example of what the data looks like from July 10th, 2025. Again, V3 is SSMIS, V4 is AMSR2. If you take a look at the zoom off the northeast coast of Greenland, you like that polynya has a slightly different shape in AMSR2, or some of the sea ice concentration maybe looks a little bit different in patches, but for the most part, we feel like it's a pretty good matching between the two. The edge looks, fairly similar. Next slide. And then, of course, when we actually look at the sea ice extent, the blue line is the SSMIS version 3 sea ice index. The orange line is the V4 AMSR2 for 6 months of 2025, January to June of 2025. And you can see the lines follow each other pretty well. The bottom plot is a difference plot. That's in millions of square kilometers, with the largest difference being just most of them are within, about 0.05 million square kilometers, so well within the uncertainty of the product, with a few spikes at minus 0.19, 0.1, but relatively good agreement for what we expect and with the uncertainty of the product. And I think that's my last slide, and it's on to Walt to talk about how the Arctic summer looked.
All right, thanks, Ann. So yeah, what I'll be talking about, is how the sea ice evolved over the summer, and this will be largely based, or at least as far as the past summer, will be based on AMSR2. We did the sea ice index. I don't remember if Ann mentioned it explicitly, but the sea ice index replaced January when we switched over starting in January of 2025. So everything in 2025 is using AMSR2 as of now. So looking at the conditions, starting with the atmospheric conditions, the summer conditions, June, July, and August. It was a fairly moderate summer, not particularly extreme. The temperatures were warmer than average over a good chunk of the Arctic, but not particularly extreme, not as much as some years. The Beaufort Sea region is, in the kind of more of the central Arctic, was actually pretty close to the average, the 1981 to 2010 average. the sea level pressure on the right, kind of not a lot of huge gradients, pretty quiet. There's not a big Beaufort high. There wasn't a big Beaufort high. So again, not a terribly eventful summer in my view. So now looking at the extent, we actually started out with the maximum in March, and that was actually a record low. That was the lowest maximum we've seen in our satellite record since that started in 1979. So we started from a very low position, but then we had like one of the slowest declines to start the spring. In April, there was very little decline, especially at the beginning of the month, almost basically flat extent for several days. And then going through the summer, it tracked along 2012, which is the current record low. It has been since then the lowest minimum on record, and it was tracking along that pretty closely until the beginning of August, and then it slowed down. And August is typically a time where the extent decline does slow. You see that in the median extent. But 2012 was unusual in that it really kept going down more steeply. And that was due, at least in part, due to a strong cyclone that went through like the Beaufort and Chukchi region. But even compared to some other years, this year slowed down a fair amount, and it ended up being the 10th lowest minimum, as you can see there. And so I'm looking at August just to kind of show one of the reasons I think for the slowdown was that we had pretty low, even lower than normal temperatures, lower than average temperatures over the Beaufort. I've rotated this to match up with the extent here. So Alaska's over on the left. And you can see a couple 3 degrees below average for August temperatures. It was much warmer than average over the Kara Sea, Laptev Sea area, but there really wasn't much ice there already anyway. So it didn't have a big effect on the melt. Now, the interesting thing, even though it was cooler than average conditions, we did lose a fair amount of ice in the Beaufort and Chukchi area between the beginning of August and the minimum. There was a lot of thinner ice, and so there was still enough energy to melt out the ice, but it just wasn't as much perhaps as it might have been in other years. And then it didn't show the pressures here, but there wasn't a whole lot of activity with the pressure, so there wasn't a lot of advection or changes in the ice motion that we saw. So, and if anything, if I recall, there was a motion that was kind of preventing the compaction of the ice cover. So we did lose a fair amount of ice in August and early September, but not as much as in past years. So looking at the minimum trend and minimum, we are kind of in the ballpark of where we've been for the last several years. One of the things we have been keeping track of the SSMIS extent, even though that's the version 3 from the Sea Ice Index, even though we aren't publishing that anymore. We have been keeping track of it internally to kind of keep track of things and see how things are comparing. And you can see the minimum extent was between Amsar 2 was 4.6 using which is our official Sea Ice Index numbers. And then with SSMIS is 4.64, so about 40,000 square kilometers difference. And that's actually right around where we kind of expect to see the uncertainty range. In previous times we've looked at it, about 30 to 50,000 square kilometers is kind of the uncertainty range that we see. And so this is 40,000, basically right in the middle. And so very, very similar. If you look at on the left the plot of the month or the daily 5-day minimum extent, the SSMIS and the Amsar 2 are almost on top of each other, very close. Really makes a very minimal difference. The trend is 100 square kilometers per year different. The percent per decade basically is essentially the same. And so we think that the Amsar 2 is sufficient to keep the long-term monitoring and have good trends and confidence in those trends. And you see the strong downward trend overall, but we are still seeing this kind of continuation starting in 2007, essentially, where there's really very little trend. in terms of the ice cover. Just the last 19 years, it's been pretty flat. Now, those 19 years are the lowest 19 years in the record. So everything starting in 2007 was below anything before that. So we're not seeing any kind of recovery or anything. But this is interesting that there's this, relatively stable period. There was a paper by Mark England and others recently that talked about this, looked at it with some modeling and showed that this is something that we might expect and isn't really surprising given natural variability. Natural variability can work for the decline and also against the decline. Here, it's been kind of helping to stabilize things for a little while. So I think a couple more things here. I'm looking at the ice age, which is an indication of the thickness. The older ice, the multi-year ice, and older multi-year ice tends to be thicker. We see on the left at 1985, and then the last 2 years on the right, things are dramatically different, obviously, as we've shown before. Much more seasonal ice, first year ice, and then even the multi-year ice is much younger. There's very little of the older ice available around anymore. And the pattern's a little bit different this year than it was last year, but similar amounts of the older ice and the first year ice. So we're in this regime of, yes, the summer minimum extent has not been changing dramatically, but it's a much thinner ice cover, so it is prone to potentially lose ice in future years. Another area of interest, this comes courtesy of Steve Howell at Environment and Climate Change Canada. He's regularly looked at the Canadian Ice Service ice charts, which are really great for seeing in the channels where the passive microwave is a little bit too coarse resolution to get a lot of detail. So they use the ice service charts to map out the conditions in the Northwest Passage. Last year was of particular interest on the left, and the northern route, which is the main channel, which tends not to clear out very completely. But last year it actually reached a record minimum and rather late at the beginning of October, and even later in mid-October, it still was almost completely clear. This year was much closer to normal. You can see in the red with the dots, a little bit lower than the average, but not tremendously. And then the southern route, which tends to be more clear and tends to become close to ice-free, has been quite low, even relative to the near ice-free conditions for the last several years, and it's kind of in that same ballpark this year. So I think that's it. So we can take some questions if there are any, or any discussion.
Thanks, Walt. Yeah, if people have questions, feel free to raise your hand or raise your virtual hand, or just unmute or type them in the chat. Thanks again, both Walt and Anne.
Well, it looks
There's
like we
a
got
question. Oh,
yeah.
yep, go
Sorry.
ahead. I was just gonna read it.
Oh, yeah, you're the host of this, maybe. What was the reason to not go with the higher resolution of the sea ice concentration? Is coming from April? I'm not sure who that is.
Oh, Capelli, yeah.
Capelli.
Yeah. Do you want to answer that, or I can answer it, Anne?
Why don't you take it, and if there's anything I want to add, I'll pipe in.
Yeah, I mean that's a good question. I mean, ideally you want to, you think the more resolution, the higher resolution, the better, the more detail you see. And that's certainly something that we've been looking at, to use the AMSR price now that there's a decent amount of data there, almost 20 years with AMSR E, that you can get higher resolution. But for like something like the sea ice index, at least for now, the important thing is to try to be consistent. And when you use the higher resolution, you're less consistent. And this is particularly true for like sea ice extent because it's a threshold. It's ice versus no ice. And the precision along the ice edge is a lot different. We have looked quite a bit at, you know, the AMSR versus the SSMI, and it's really there's pretty significant differences, you know, hundreds of thousands of square kilometers even, because of the way that they are able to image the ice edge. And so what we decided to do was to try to preserve the longer record and then move forward with AMSR 2 and make that consistent. Ultimately, at some point, what we'd like to do is, you know, use the higher resolution AMSR as kind of the baseline and then maybe process back to try to match that up. It's something we've started looking at, but we haven't had the resources to go into too much detail yet. So yeah.
Yeah, and it's a little harder to take something that's low resolution and make it better resolution than it is to take a higher resolution image and degrade it. So it was just, you know, we didn't have, we were very, yeah, so that's kind of what we decided. Also, we were pretty short on time this summer with the announcement that the SSMIS was going away. It was sort of sudden. And this is kind of, we've been working towards, we're like, well, you know what, we got, you know, about 4 to 6 weeks to get this done, and this is what we can do. And also, you know, it keeps things consistent. But as Walt said, we are investigating going the other direction, but it'll be a bit before we can put that out.
Yeah, and then I think Dave Bailey asked what the September mean was. Yeah, and I probably should have put that in there as well. It was 4.75 million square kilometer. That's in our sea ice index, our spreadsheet as well, and that was the 11th lowest. So the daily minimum was basically tied for 10th. September ended up being 11th lowest at 4.75 million square kilometers.
So can I ask a follow-up on that?
Yeah.
So you said the daily mean, there was a slight difference between the SSMIS and the AMSR. Do you think the monthly mean would be different in the same direction? Does it cancel out with different days, or have you worked out what the SSMIS would have been?
Yeah, that's a good question. It is smaller in the monthly mean because they do tend to cancel out. You know, you see kind of like the ups and downs of the daily averages based on the different conditions. So the monthly is less. We didn't. I don't have that offhand for earlier periods. I forget exactly what we looked at for September. Unfortunately, there was like a power outage at the Navy Center, the Fleet Numerical Meteorological and Oceanographic Center, where we get our data. So the data, they stopped delivering data. I think it was like September 24th. And so we haven't been getting data. And then with the shutdown, the data is interrupted as well. So basically, we don't have any data for the last week of the month. So I don't think we could really do a good average for September. I thought about trying to do that, but with the missing data, I don't think we'll really get a very good average, especially missing at the end of the month. So unfortunately. Yeah, and just responding to the next question about the advantages for coastal regions, it's definitely something that it is definitely an advantage there because you get the smearing and the kind of the land, the mixed footprints of land and ocean that can look like sea ice. And so we tend to see sometimes these false ice patches. And so certainly that is something that would be improved with a higher resolution.
Yeah, do we have one more question from Charles? Do you want to unmute yourself?
Yeah, thanks. If I understood correctly, when you were talking about the differences between SSMIS and AMSR 2, it was around 40 to 50,000 square kilometers. But it looked like you were dealing with that as kind of an absolute, and as a fraction of the sea ice cover, it was a much worse performance as you were getting into the September timeframe and there's less ice cover. Is that the way that you all think about this, or Do you look at a fractional error versus the absolute?
So we looked, I mean, the percent error is something we have looked at, and it does get worse in summertime as it decreases. Anne showed, we did an evaluation that Anne showed, like January through June, or yeah, January through the end of June. And June is it kind of starts getting kind of bad, like June and July, because of the surface melt, the differences in how the different channels respond to the meltwater, the different times of day that they're seeing. So there's various effects there that are worse during the summer melt season. Now, when you actually get to September, which wasn't in Anne's plot and probably could have shown one of those, but when we get to September, things come back. And they're better in September as things freeze up. The freeze up is better. So September is actually not too bad. It's closer. You're generally, we're hoping to be within like 1%. It does get a little higher in the summertime because the ice it's decreasing, and then the errors are increasing. But when we're, so the September minimum there was about 1%, what we saw there. And that's kind of, once we get to September, it's about 1%. And then it can even be less in the wintertime, as the total extent is higher. So the error, is focused a lot on like we showed on the ice edge. And so the bigger ice edge you have, the less percentage error. So I think both are important. We want to try to get as close as we can absolute value, but as well as percentage. And so that's definitely something that we are concerned with. And I'll just note, this is a preliminary, we did this kind of on the fly fairly quickly to make sure we could keep the data flowing. It is something, there are some thoughts and things we could go back when we have a chance to try and improve and refine. And so we will definitely be looking at that when we get a chance. But this was the best we could do at the time, and I think it's quite good. At least I'm pretty satisfied with it. So
Great, thank you.
Yeah, that's awesome. We should probably thanks very much again, Walt and Anne. Really nice to see that. Yeah, that time series come together. We should probably move to our second speaker, so we have a little bit of time to also ask some questions there. So if you want to pull up your slides, Joel.
All right, can you see my screen okay there now?
Yep.
Yes.
All right, thank you. Thank you for inviting me to come. I don't have a talk title, but I'm going to talk a little bit about both the observations from communities of ice and serving products back to communities through the SIKU app. So we're the Arctic Eider Society. We're an Inuit-led charity based in Senekiluaq, Nunavut. Get on my slide. We're out in the middle of Hudson Bay on the east side on the Belcher Islands, Hecate, which are out in the heart of Hudson Bay and a very unique place for sea ice. I'm not Inuk. I'm from Newfoundland originally, but I've had the privilege now of working on the ice with local hunters for 24 years. And it's a pretty amazing place with flow edges in every direction, different oceanographic regimes and lineas on the ground. And so we're a charity, and Seneca Army used eiders for their clothing and food. There's a film still on Amazon if you want to check it out about that background. But we do more than duck stuff, and eiderdown is the warmest feather in the world, the best of nature's technology and Inuit innovation. So we're really about how do we bring together the best of Inuit knowledge and science to work together. And just because technology is new doesn't mean it's better. So how do we really help Inuit knowledge and science work together for the benefit of Inuit self-determination? Through our programs on the ground, we have a bunch of different people working here and across the north on culture programs, protected areas, ice monitoring, and a few other things. Lucasy is our leader and chair, and has a long history. He won the Polar Science Award a couple of years ago, and has been working with communities from all around the region through his work with Voices from the Bay. This summer, he indicated it in his 75 years, this was the coldest spring and summer that he'd ever experienced here, which might have been part of the reason for that slowdown. So we have a network with different communities in the region working together to kind of put together the pieces to help get the big picture about what's been changing. We do a mix of oceanography, but and wildlife monitoring. But today I'm going to talk about SIKU, the Indigenous Knowledge App, which is an app that we have created based here, but it's now being used across the North. And it was inspired by elders like Peter Katuk, who said, it's time for the harpoon and the computer to work together. How can we engage youth and use technology to help show the value of Indigenous knowledge? Peter was a hunter that was out at the flow edge every day in winter hunting seals. And one of the observations he had was that he was noticing major regime shifts in the diets of seals, shifting from fish to more shrimp. And the typical approach was that the response from academics was like, that's interesting, but we need the data, and this is kind of anecdotal. So, you know, scientists would spend 5 years coming up with funding, doing the study, and come back to Inuit and say, guess what, you were right all along. And which was kind of frustrating for Inuit, and say, why didn't you believe us in the first place? And Inuit have had a complex system of peer review among hunters and elders about the changes they see, but it was based on oral history. It wasn't really written down. And so the idea behind SIKU was, you know, how people were starting to use social media. And if you could tag animals or Indigenous environmental terminology in the same way that you could tag people on social media, then the data that's always been behind that knowledge could be documented and shown to help provide equity for Indigenous communities across the table from government and academics. And so that's kind of a little bit of the history from where SIKU came from. It's a mobile app. It's an online web platform. It works completely offline. There's some of the map services work offline. And then when you get back to town, you can upload your posts and videos and content to share overall. So the first study on SIKU was about seal diets, and kind of shows that how a post gets made and you can tag the wildlife, you can tag the stomach contents, you can take measurements, you can tag the habitats. In this case, it was plinias, flow edges, and breathing holes, and help show the data that's always been behind Indigenous knowledge. SIKU's really taken off in recent years. It's been growing exponentially. There's over 40,000 users. There's actually over 140,000 posts now since we updated the slide. There's over 1,000 active users per day, and there's over 100 active projects that are using it for a wide variety of purposes related to everything from ice monitoring to wildlife monitoring, guardians programs, and protected areas, and community-driven research. It's built around Indigenous data sovereignty and guiding principles, so it's not an open data platform. The hunters fully own and have access to their data, and there's an informed stewardship approach. There's very flexible settings for privacy, so you can keep something private to yourself, share it with whoever else is on SIKU. It can also be shared to vetted projects, where the members of those projects would be vetted. And as a framework to really help promote a safe place for sharing Indigenous knowledge as well. And the data can be exported in real time. One of the most fundamental and unique parts of SIKU is the use of Indigenous environmental terminology as a classification system or taxonomy. And so that ranges from Indigenous place names on a decolonial base map to wildlife cross-referenced across different Indigenous dialects. And most relevant here, I think everybody knows that Inuit have a lot of words for snow and ice. And it's more than just words, it's more than just language. Being able to mobilize this, put it in people's hands on the land, on the ice, is a big part of it. But it's more than language. This is their classification system. A lot of the man ice, the ice manual is based around icebreakers and shipping and avoiding Titanic sorts of situations, whereas Inuit classification has come from traveling on the ice, how it changes through the seasons, and how wildlife use the ice. And so being able to develop that classification system in a taggable way with profiles that are cross-referenced across different communities' dialects, so that when you know you're talking about a plinia, we call them Ikirasak. Up north, they call them Sakvak. And so knowing that we're talking about the same thing and can tag the same thing, but it shows in your local dialect based on the community that you pick. So that's kind of the really unique thing, showing that Indigenous language can be used as a taxonomy or a classification system. So I used to be an academic. I did a PhD in ecology and math and was all about measuring things, and now I've been really helping Inuit to show that Indigenous knowledge is measurable. It's not just anecdotal. So this is the mobile app of SIKU, and this shows, you can see we have a base map. The SIKU ice map is a unique map that brings together ice charts from the Canadian Ice Service and other ice services, and it processes radar. I'll show you some of the services a little bit later. It processes both Sentinel and RCM, RadarSat Constellation mission data to serve it to communities and to show the moving ice. And so this is a really important product to put into people's hands so that communities have it for trip planning and when they're on the ice. And then the local observations from individual hunters that they make are put on the map as a part of that as well. And this is an example from Josie here. And so just as one example, before SIKU was even public, Jonasy is one of the hunters here that really helped develop it. And he made a post near town about a crack in the ice that you can probably see on the image here. It kind of goes down like this. And he was trying to make a decision, do I cross the ice to go to the flow edge to try and get seals? But he knew that it looks like Tukilik, which is a tidal crack that's going up and down with the tide. But he knew that this was a different kind of crack called Sihumak, which is moving side to side instead of up and down. And if the wind comes perpendicular to it, it can break off, and then you can require search and rescue. And so he made this post, putting it on the map, sharing it with youth in the community, and he was able to actually get before and after pictures, and it linked up to the Sentinel-2 visual imagery the day before and day after. So you can see that if he had crossed, he would have required search and rescue. And so this is just one post showing how that knowledge transfer can happen. Also showing that Inuit can help do ground truthing and of satellite imagery and products. And now we've started the annual SIKU Ice Watch. It's been on the go for 5 years now. This will be the 6th winter, and there's over 5,000 posts now since this was updated from communities all across the north, and including Greenland and Alaska, and really showing that it can not only contribute to local safety and knowledge transfer, but can show how Inuit and Indigenous communities can do large-scale climate monitoring at scale for the whole Arctic. And so within this, there's a lot of information about more subtle ice changes, but also like some areas where the cracks break up every year, and the dynamics of those areas. Auyeraks are the cracks in the spring. And so those are pretty consistently shared all across the north. And so how it can really help Inuit with knowledge transfer and play a leading role in climate research. I won't get into too much of the wildlife side, but SIKU really helps hunters track their harvest, track the posts that they made and their activity on the land. It's map services, so it's a GPS, it works offline, you can track your trips. But I just wanted to touch on the satellite products that we have on there for the map. So there's the base map, which combines both topographic and hydrographic charts. And we've been bringing in a lot of community bathymetry into those maps to help Inuit use both the land and the water and want the same map. And so we've generated this product. We actually subtract the topographic and hydrographic coastlines to add kind of an extra intertidal layer in a cautionary way, and have been updating that with community bathymetry as well. The Indigenous place names are there, and so Sentinel-2 comes in, which is really helpful here because we're fairly far south relative to other Inuit communities, and we get a decent amount of daylight. And so it can be very helpful for identifying ice features on good days. But of course, up north and when it's dark and when it's cloudy, the radar is really important. And so we have a pipeline that brings together Sentinel-1 and RCM data that we're processing on our own tile server that can get that into the hands of community members. And as I mentioned, that helps produce the derived product, which is the ice map, which has the ice charts showing the landfast ice and the flow edge. And there's a layer that processes radar to show how rough the ice is for the landfast ice platform. And it's getting a lot of access. in just 1 year, there was 28 million tile requests from all over the north, and you can see that the Tuavik Barrow is getting a lot. Nunatsiavut and Greenland actually is requesting most of that imagery, which is interesting. We've never run a workshop there. There's almost 6,000 users in Greenland now, just organically on the app without projects. Just quickly, we've been doing some work on machine learning to help identify polynyas. The ice services, ice charts don't include those features within the landfast ice, but those are obviously really important for safety and transportation for communities. And so we've been working to train through drone work and groundwork and using the Sentinel-2 visual imagery to draw polygons around polynyas to try and train machine learning algorithms to identify polynyas from radar imagery so it can be served on a regular basis. And we've made pretty good progress on that. It's not operational yet, but we're working to operationalize that in the next year or so, where we would kind of show a progression of how they're changing. Not every day is great for identifying them, but if by combining multiple days of imagery, we can serve a product with a fairly decent level of confidence about where those polynyas are in a cautionary way that people should be careful when approaching those areas. And we're looking to build a more general hazard map. So this is kind of what the ice map looks like now in the background with the Landfast ice platform and with the community posts, and putting polygons like the polynyas in red there, as well as cracks and the different kinds of cracks in the foliage that we would be looking to in the future combine into a hazard map layer that could be there on top of any imagery. So I think I'll stop there. I could get into all the different projects that are using it for wildlife and the types of information that are coming. The transportation data is very rich for land use and occupancy that can kind of show not just where the posts were made, but where people went. The mapping sort of work that can show some of the climate change work for fisheries, and I'll leave it at a big part is helping visualize the data in an Indigenous lens is a big part of what SIKU is helping do on the project side to help communities run their own projects and make their own decisions and have the data to be able to mobilize that for their own decision making and self-determination. I'll leave it there. Thank you.
That's awesome. Thank you very much. As before, if anyone has questions, they can raise their hand or post them in the chat. I also have some questions, but we got to see if anyone else does. I mean, I guess the kind of like maybe overarching question I have, or maybe most basic question is, yeah, if you could say anything about how you think scientists, I guess, especially for the sea ice stuff, which this group is normally focused around, scientists can best interact with this, I guess, both kind of in the terms if there's, yeah, like ways that we could use it, but also ways to contribute. I don't know, I guess I'm curious if you have any ideas about what that should look like.
Yeah, for sure. I mean, I think in terms of the service delivery side of SIKU, as you're getting different imagery and there's no microwave data in there. So I think there's a lot of other remote sensing data that we can look at combining into products and drive products to serve out to communities for safety and situational awareness. On the data side, we have like SIKU is not open data, and so but users can be members of projects and choose to share posts to projects, and those projects need to respect Indigenous governance structures. For the Ice Watch, there's a stewardship that means people are sharing that data to the Ice Watch project. Right now, it's not set up for research. It's set up so that that data can be used to serve back products to Indigenous communities for their own benefit and safety. And we're looking at how we can expand that to be more open, where people give the permission to be able to use it while still making sure that we respect Indigenous data sovereignty on the platform. The most complicated part of figuring that out is because it's so interjurisdictional. Like if we're going to get the rights to use the data, then like we'd have to apply for licensing in like at least 16 jurisdictions. And we don't have the capacity to apply for that many research licenses. But it's a challenge, but I think there might be a way to simplify that. I'm not sure, but we are starting to, within the stewardship of the Ice Watch, we're able to start doing like key performance indicators, like what's the coverage, how is the coverage changing between years, and have some preliminary outcomes. And I think there's some key indicators in there, like the IUROX, the cracks in the spring, like, and looking at, you know, consistent areas and how they break up and the chronology of that and what it looks like between years that might be interesting to correlate with the sea ice minimum data and how it looks more at a local level. So I think there's a lot of potential there, and it is possible to get the rights to use some of that within a region, so it doesn't have to be at scale necessarily. It's something we're trying to figure out a little bit more. And so I'd flip that a little bit and like be curious to get your thoughts on how you think some of that information might be able to help with your objectives too.
Yeah, it's a good question. And I think those are definitely things that, I mean, obviously lots of people have different interests, but I think that understanding how the changing conditions relating to cracks and breakup is something that, yeah, we're motivated by and interested in. And yeah, I guess I was also curious if, especially like, because you were talking about the Ice Watch, is that something that like scientific observations can also, or like observations that scientists are making can also tie in? I guess one thing I'm thinking of is, I don't know, like if you're familiar with the like ASSIST program, which is historically more like ship-based, but like visual ice observations are, it's a place that has consolidated visual observations from ships, both in the Arctic, but also in the Antarctic. So I guess I'm wondering if there's like a place for those types of observations also to contribute, or if they're of a different scale that's maybe not as useful, but.
Yeah, no, for sure. And I didn't really get into showing you exactly like the details of creating a post, but in addition to like being able to tag indigenous taxonomies, there are the measurement tools. And so a lot of those posts also have like ice thickness measurements and snow measurements and things as well. And we also, I'm not sure if folks are familiar with Smart Ice, but we're their main service provider to get their products out to communities where they're using Smart Comatic and Smart Buoys to measure ice thickness through the winter, and the data's on there, and that can kind of be centralized through SIKU if that's something that those communities want to share that data out as well. And there's ways we can add, it's pretty easy to add new features in there if there's other sorts of measurements and scientific observations that people want to add. We've been trying to put in, there's a whole weather tab. SIKU's basically got this whole separate weather app in there now, which brings together the marine forecast, the daily Northern Lights forecast, a windy product, tide forecasts, and Smart Ice data in one place, so communities can get all their weather information in one place, and it'll link that weather data to the posts they make as well for kind of bigger analysis and stuff. So remote weather stations that researchers have that could be served out to communities that can be linked to their community forecasts or other types of observations is definitely something we can think about putting into the platform as well.
Yeah, that's awesome. That's really good to know. And hopefully people can take the time to poke around and see what the app looks like to kind of think about data they have that might be useful and how we can collaborate better. Yeah, sounds very relevant. Yeah, and really exciting to hear about all the different things that you guys are doing.
There's a bunch of oceanographic tools in there too. So there's like CTDs and water sampling, ice core sampling, and it helps you document the data and the metadata. And even you can, in the back end, you can add lab results and stuff afterwards. And so some of those, there's a lot of CTD casts across the north that might be able to help tie into other sorts of indicators and that sort of thing. Time-lapse monitoring stations that we use a lot for ice monitoring, drone ground truthing. So there's a bunch of research tools in there as well. And we've thought about, there's some drone work that could even potentially like add the generate map tiles from like the higher resolution imagery that adds additional layers to the satellite imagery and products on there and stuff. So we're open to any and all ideas and happy to explore them. Some things take longer than others, but yeah.
That sounds great. Yeah, hopefully we can be in touch more. I know we are at the top of the hour. So I don't know, Meredith, do you want to wrap up the meeting or anything else?
Sure, yeah. We'll post the recording on the ARPIC website. Thanks everyone for joining. Thanks, Joel, for your really interesting talk. I think Joel's on the IARPIC website because I just approved his account. So if you want his email, it's there. Or if you want to post it in the chat too, you're welcome to do that, Joel, if people want to follow up with you as well. And I think with that, we can end the meeting. Yep, thanks, Joel. I see you put your email there. So thanks again, everyone, for joining. It's a good meeting. Thanks, Maddie, for facilitating.
Yeah, of course. Yeah, thanks again for the great talk, Joel. We appreciate it.